Hello and welcome to the setup for standing waves on a string. Now, as you can see right here, these are the items that we need in order to perform this experiment today. Now, the experiment itself in the items list includes two other types of string, but in the actual experiment, for whatever reason, those two types of string aren't used, just one. However, what you'll need is a power amplifier, two clamps, one clamp to clamp the pulley to the end of the table, and one clamp to clamp the string vibrator to the end of the table. Also a string vibrator, leads to attach to the power amplifier, string, and also a set of weights. Now the purpose of this lab is to explore standing waves on a string. So I'll show you the correct setup of the lab in the next section of the video. So this is the proper setup for this experiment. You have your data acquisition system right here, which is hooked to the computer. This right here is used to change the frequency and also provide power to the power amplifier. The power amplifier itself is connected via two leads. Here, traditionally, red is considered to be positive and black is considered to be negative. But in this particular case, that doesn't matter because this is alternating current and there is no positive and negative per se. You have a string attached to the end of the power amp or to the string vibrator. This is approximately 1.2 meters to a pulley that hangs off, that has a mass, in this case is 25 grams, hanging off the end. Now in this particular setup, what I've done to help provide some stability for this is to actually clamp a meter stick to the end. That's because of the thickness of the table, and the clamp, as per experiment, is a little problematic. So as you can see, just from a full setup standpoint, get a little bit of perspective here. That's what you're looking at right there. Now your standing waves will be formed between where the string ties into the vibrator and to where the string hits the top of the pulley. Now in the next video, I'll show you what happens when you operate this. So let me show you an example run. Now this is the first part of the first part actually, and it has you hang 150 grams total off the end. You want to measure the distance between the pulley and also the string vibrator. Okay, that is to the knot right here. So if you take a look at this thing on edge, I have it set to 1 hertz from a frequency standpoint. And you can see it very, very slowly oscillating up and down. It does 1 cycle in 1 second. So 1 hertz, remember, is 1 complete cycle every second. So that said, the terminology that your lab uses is segments. So a segment would be 1/2 of a wavelength. Now standing waves, remember, require integer number of half wavelengths in order to work between the endpoints or the boundaries. So one boundary is here, one boundary is here. Now when you get one segment or half of a wavelength on here, we call that the fundamental frequency. So what I'm going to do is to adjust the frequency of my power source here and set it so that you see. So let me show you an example run. Now this is the first part of the first part actually, and it has you hang 150 grams total off the end. You want to measure the distance between the pulley and also the string vibrator. Okay, that is to the knot right here. So if you take a look at this thing on edge, I have it set to 1 hertz from a frequency standpoint. And you can see it very, very slowly oscillating up and down. It does 1 cycle in 1 second. So 1 hertz, remember, is 1 complete cycle every second. So that said, the terminology that your lab uses is segments. So a segment would be 1/2 of a wavelength. Now, standing waves, remember, require integer number of half wavelengths in order to work between the endpoints or the boundaries. So one boundary is here, one boundary is here. Now, when you get one segment or half of a wavelength on here, we call that the fundamental frequency. So what I'm going to do is to adjust the frequency of my power source here and set it so that you see one segment or one half of a wavelength. So let me here. So as you can see here, and it's sort of gradual, but you can see the string is vibrating a little bit faster. See how it's moving a little bit faster. So now, let me increase the frequency. So the goal is to find just the right frequency so that when a wave travels from the vibrator to the pulley, the tension inside of it is such that you get half of a wavelength on the string. And if you take a look here, that looks like half of a wavelength. I think I can do a little bit better in adjusting. So let's see what I can do here. So the goal is to get basically the biggest amplitude or the biggest height of your standing wave here. So you can see the standing waves right there. Now at this point, what you would do obviously is to record the mass, the length, and the frequency. And what you're going to notice as you do the lab is that the next standing wave, where instead of having one segment, you have two segments, the next standing wave is going to be at twice this frequency right here. One in which you have three segments would be 3 times that frequency. Okay, and if you look at the equation for the speed of a wave and fix the speed, then and play with it, you'll discover that that's the consequence of it. Okay, so this is a sample run, like I said. In the experiment, you're going to do this for 1 segment, 2 segment, 3 segments at 150 grams, and then you're going to start off at 50 grams and add mass until you reach 250 grams, looking at how tension affects things. Hello and welcome to the theory section for Lab 2, Standing Waves. Now, in the following picture, you can see a rough sort of drawing of the experiment that we've done. Here's your string vibrator, here's the pulley, here's the hanging mass that provides tension for the string. And between the knot on the string vibrator and where it touches the pulley here, you have the length of the string. Now, the goal of part 2, part 1 really covers material that we've already talked about. The goal of part 2 is to try to empirically find the mass density of the string from data that we've taken. Now, if you recall in the videos dealing with oscillations and waves, we came up with a relationship between the speed of a wave and the properties of a string on it, rather the speed of a wave on that string, that looks like this. It's tension divided by the mass density, square root of, so this is the speed. Now, first of all, I'd like to point out that in this particular lab, instead of using mu to denote linear density, they're using alpha. Now, I sort of warned you guys about this. I said sometimes they use wavelength, or lambda rather, not wavelength, for linear density. So this is just one of those examples where they've chosen a different symbol, which may or may not be used. We use mu, they use alpha, whatever. So I'm going to, in this particular derivation, continue using mu since that's what we're familiar with. Now, we also know from our discussion about waves that there's a relationship between the speed of a wave, its wavelength, and its frequency. Now, for part 2, what we're doing is we're combining these two equations in such a way that we can get something that we can relate to a plot. Now, our plot that we're looking at making is that of frequency squared versus mass. So, on the y-axis here, we'll have frequency squared, and on the x-axis we're going to have mass. Now let's not forget that our frequency is measured in hertz, but our mass in this case we want to make sure that we use in kilograms. And obviously that's going to be true for any instance of this particular equation that we end up using. Because remember, we work in the MKS system, not in the system that uses, centimeters, grams, and seconds. So anyway, I'd like to relate these two real quick to each other. Lambda f is equal to the square root of t over mu, and talk about how these things relate to stuff that we actually measured in this experiment. Now, first off, let's talk about the tension. Now, the tension is a consequence of the mass that's hanging off the end. Now, we know the mass, as a consequence of being suspended in a gravitational field, has a weight Fg. Okay, so this is just m times g vector would just be g, times minus y hat. But it's this balance between this and the tension here that keeps this mass at rest. And the tension here is going to be the same as the tension here, because we know that at all points inside a string the tension is the same. So really what this means is that these are equal to each other. They're just pointing in opposite directions. So I can, for the tension, just put in m times g, and I'm okay. And that's one of the things we're going to do, is to put mg in here. Now, next, I'd like to also point out that we're not directly measuring the wavelength in this experiment, but when you have a standing wave, what that means is that you have an integer number of segments on your string. Now, the data that we're plotting here deals with 4 segments. So one segment is half a wavelength. 2 segments is a full wavelength. So what that means is that you have 2 full wavelengths that sits on the string. So L in that case would be 2 full wavelengths. So if I want a relationship between the wavelength and actual measurables in this particular experiment, it's this right here. Lambda is going to equal to L divided by 2. So if I put these things in, I have L f divided by 2 on the left-hand side. And on the right-hand side, I have the square root of mg over mu. And then I take and I square both sides. If I do that, I have an L squared here. I have a frequency squared here. I have a 2 squared, which is 4 on the right-hand side. This is just mg over mu. And now what I'm going to do is I'm going to move everything that's not frequency squared over to the right-hand side. So the frequency squared is on the left-hand side. On the right-hand side, I have 4 mg divided by L squared times mu. Now we're plotting the frequency versus the mass. Okay? So what I'm going to do, or actually frequency squared versus the mass. So I'm going to put in parenthesis on the right-hand side everything that's not the mass. And if you think of this as the y-axis and this is the x-axis, then really what we have is y is equal to some constant, so this is your slope, times the mass. So when you plot your frequency squared against the mass, you should get something that's going to look a lot like a line. So once you get that line, what you're going to do is to use Excel or whatever it is that you're plotting stuff in to do a best fit. Okay, so you'll find the slope of your line doing a best fit. You'll get m. Whoops. Yeah. So you'll find m. I say m. We've already used m. What's a good? I'll just call slope. You'll find the slope. Okay. And that slope is going to be equal to this. So empirically, you're going to get this by fitting data. All right. So your slope is going to equal to 4 times g over L squared times mu. G is just 9.8 meters per second squared. L is in your data for your experiment. And so what that means is that having the slope, you can easily solve for mu. Okay, so in this case, mu is going to equal to 4g over L squared times the slope. Okay, so that's the theoretical section for this particular lab, and I'll see you later.